Okay, this is calculus limits derivatives, day number 4, L'Hopital's rule, indeterminate forms. I'm going to skip a few problems here that we're supposed to be doing on yesterday's homework. Indeterminate forms they come out as something other than undefined, aka infinity, or some finite value, right? So we like numbers like 4 or 2 or 0. We don't like values. An indeterminate form would be 0 over 0, or infinity over infinity. And there are many others. We could have negative infinity over infinity, etc. Those are forms that we don't like, but L'Hopital has helped us to resolve. I'm not going to talk much on this slide. These are some other indeterminate forms. Did you know that infinity minus infinity is not 0? It's infinity. I know. And infinity plus 1 is just infinity. Yeah, I know. And 0 times infinity, guess what that is? Infinity. I know, it doesn't sit well, does it? I know. That's all math language is. It's made up. So, on an AP exam or IB exam, the first thing you need to do is plug in a value, right? Plug in where the limit is approaching. So if I plug a 0 into the first one, I get sine of 0 over 0, which is 0 over 0. You have to. I'm telling you right now, you need to write that. You need to show that you have an indeterminate form, 0 over 0. Now, we know the cheat, right? This limit equals what? 1. But we're going to use L'Hopital's rule. What I would suggest on your test is to either write like shorthand for L'Hopital is being applied, and then take the derivative of the numerator and the denominator. Don't be a fool, though. Somebody's going to do the quotient rule here. They're going to make their life not cool. Don't do the quotient rule. Just take the derivative of the top, derivative of the bottom, leave them where they are. Derivative of sine is cosine. Derivative of x is 1. And if I plug in a 0, cosine of 0 is what? 1. And I get 1 over 1, which is 1. Sweet. Thank you, L'Hopital. You're very nice. Yeah. Awesome. Okay, catch yourself back up, kid at home. Over 1 equals 0 over 1. So we get 0. And we knew that. That's another special limit. Okay, let's pick 3 or 4. Let's do 3. How about that? Because both of them are going to take up a little bit more space than we have available. Okay, why would I say that this limit is approaching 0 only from the right? What function tells you that? Which of those two functions doesn't exist coming from the left? Natural log, right? So if you see that, know that one of the two functions is limiting what? Limiting the limit at that value. No pun intended. Okay. So if I plug in 0 into the natural log, what do I get? I'm going to get an error. Right? What does the natural log look like? Well, it's got a vertical asymptote. Okay, here's the natural log of x. It's got a vertical asymptote. However, this is not natural log of x. This is negative natural log of x, so it's a vertical reflection. So what would that graph be approaching as x approaches 0? Infinity, right? So if I plug in a 0, negative natural log of 0 over cosecant of x. Yuck. I don't want to think of cosecant of x. What do I want to think about? 1 over sine of x. So what would be the sine of 0? 0. So what is 1 over 0 equal to here in the denominator? Because I get positive infinity here, and I get a positive infinity here. L'Hopital's rule applies. 1 over the sine of 0 1 over 0 we could call does not exist or positive infinity. Right? If it were the negative cosecant of x, then it would be approaching negative infinity. Right? You remember secant? It goes like this. Right? Maybe that's not how you remember it. That's how I remember it. I remember it like this. I'm glad that people at home can see that, because that was the worst dance move ever. Right? You're doing this one. You're like, oh, yeah, cubic, quadratic, cosecant. Yep, you at home, you missed out. That wins dance-offs at weddings. Okay, so infinity over infinity. That is a indeterminate form. L'Hopital's rule applies. Okay, now it's going to get kind of ugly here. Let's get ready for ugly. Okay, what is the derivative of natural log of x? 1 over x. So I'm going to apply L'Hopital's rule. Okay, so I'm going to have the limit as x approaches 0 from the right of 1 over x in the numerator. Don't forget it's negative. So I have negative 1 over x. Okay, now in the denominator, does anybody know the derivative of cosecant x? Remember from yesterday? Cosecant, it was negative. Cosecant, cotangent. Oof. Oof. Okay, let's see what we can do with this. Negative cosecant cotangent. Oh, that's gross. Would you be okay if maybe I turned this into 1 over sine and did the quotient rule with 1 over sine instead of cosecant? Yeah, let's do that. So instead of taking the derivative of cosecant, I'm going to take the derivative of 1 over sine x. Why is that doing that? There we go. So let's take the derivative. Well, okay, so everybody's on the same page. Are these two equivalent? Can we agree? Okay, let's take the derivative of 1 over sine x, because I don't really want to work with cosecant and cotangent. It's just ugly. So quotient rule. Bottom times the derivative of the top. Well, that's nice, because that's going to be 0. Minus top times the derivative of the bottom. Okay, that's too easy. Over bottom squared. Isn't that just negative cosecant cotangent? Yeah, right? Because all this is negative cosine x over sine x times 1 over sine x. That's cosecant. That's cotangent. Right? Same thing. Now, why would I put in terms of sine? Well, I'll show you why. Sine and cosine. Because one of our special limits comes out to play. All right, I got a negative and a negative. So is everybody okay with the fact that those two are just going to negate? Thank you. Okay, cool. If I have cosine x over sine x times 1 over sine x, you might see this right away, you might not, but what's the limit as that goes to 0? 1, right? X over sine x. Are you with me? Or I could go ahead and multiply everything by the reciprocal of the denominator. Instead of dividing by this, I could multiply by its reciprocal. So that'd be sine x over cosine x times sine x over 1. And as I duplicate that in the numerator, right, the denominator disappears. I get this in the numerator. I see sine of x over x. Well, that's going to go to 0. Excuse me, go to 1. And what is this thing? Tangent. Okay, so let's talk about that for a second. Limit of, as x goes to 0 from the right, of tan x times sine x over x. Everybody agrees that's going to go to 1. So we just have to determine what the limit is of tangent as x goes to 0. What is that? Yeah, 0. Look at the graph of tangent. Here's tan x. As x approaches 0 from the right, it's going to 0. So this equals 0. I want to show you something on Desmos that you can do. And I'm probably going to record this at home. I think they can see anything on the screen. Let's go with Desmos. And so I can remember what the problem was. Here we go. I'm going to type in our function, negative natural log of x divided by cosecant of x. As x approaches 0 from the right, what is that limit? 0. You can always go on Desmos. I would suggest this. Go on Desmos, type in the function, and see what happens as x approaches c, whatever that value is. As it approaches 0 from the right, look at that. It approaches 0. So if I looked at the next example, which is x natural log of x, that answer is 0 as well. If I wanted to see sine of x over x, we know the answer to that. That's 1, right? Look at that. It approaches 1 as you approach 0. Okay, this is a good way just to check your work and see whether or not your answer is legitimate. 1 minus cosine x divided by x. That approaches 0 as x approaches 0. Cool. Okay. Most of what you're going to be doing today in your assignment is manipulation of algebra. And I'll tell you this. What we did were our warm-up. Those of you at home, good luck.